All right, we're going to tie up the module on energy right here, just a few loose ends that we're going to talk about. And then I'll sort of go through a bunch of different types of energy that you'll see, sort of like an energy in your everyday life kind of thing, and those sources. And after that, and after those examples, that should tie everything up in this module. And we'll move on to the next one, which will likely be rotational motion. But until then, we're going to talk about machines. So we've talked about work, power, kinetic energy, potential energy. And what we're going to move to next is essentially the applications of these ideas and where you're going to see them sort of out in the wild, so to speak. A machine is essentially a device that multiplies force, and it could also change direction, or it could only change direction of the force. So it's essentially a device that multiplies force, changes the direction. The principle underlying every machine is the conservation of energy. So it's the whole idea of energy going into a machine, and then you got energy coming out of the machine. That has to be conserved, but the machine is going to multiply it at the cost of something else, or the machine's going to convert it into another form, something like that. For the first example here, let's just consider the simple lever. So the whole idea, for those of you that maybe work in a auto body shop or a metal shop or something, if you're trying to like get a bolt loose, or if you're trying to screw in a screw with a screwdriver, it's easier if you have like a big round handle, because the fatter the handle and the bigger your radius is that you're trying to turn, the more energy essentially you can get into your system. Same kind of idea here with a lever. So with a lever, when work is done on one end, well, the other end also does work. So if you think about what the definition of work is, it's a force over a distance, right? Well, if we apply a force, for example here, if we apply a force to one end of the lever, well, we're going to move it through a distance, right? So if it started up here and we apply this force, we have both pieces, both ingredients of work. So work is done here. This is their input. Okay. Moving one side, work's done on one end. Now, if we think about the other side, while the side over here on the left goes down, the other side on the right actually moves up. You'll notice that the distances are not the same. So we also have this big distance that we're going through. And then on the right-hand side, we have this very small distance that we're going through. So even though the distances are not the same, the proportions will still work out, because we also have to consider force. So when work is done on one end, the other side also, there's a force being applied, as you can see here, and it also travels through a distance. And the directions also change. So we pointed that out as well. One side goes down while the other side goes up. Now, if we think about if we put a load on one side, if we want to lift something heavy, the idea is if you make a really long lever arm on a lever, you can actually lift something really heavy. So if we push down on one end, so like this, okay, a load is lifted. So maybe we're lifting, I don't know, a large boulder that sits on the end here. So there's our load. Okay. Now, you'll notice that the fulcrum, which is this thing here, the thing that the lever is teetering on, the fulcrum changes the distance traveled by the ends. Okay. So on one side, on the left side, we have a very long lever arm. me clean that up. There we go. A very long lever arm. On the other side, you have a shorter lever arm. Okay, and that the length of your lever arms depends on where your fulcrum is. Now, when the fulcrum of a lever is really close to the load or relatively close to the load, like it is now, it's closer to this boulder I've drawn. What that's going to do is essentially going to set up the proportions, right? Because we have force times distance, which is work in. We have work out, which is also force times distance, but you'll notice that the proportions are different. Okay, so when this lever is close to the load, a small input force, notice how small my input force is, baby F. A small input force will produce a large output force. Notice how big the output force is. So what this means is if puny Dr. Roten is standing over here and he uses his puny little nerd arms and pulls down on this lever, he doesn't have to apply much force, little f, to get a really big force out of this machine. Okay? So that's the whole idea of a machine is we can put in a little bit of force, but then we get a lot of force out. But there's a cost, okay? That comes out here in the second sentence. So this is because the input force is exerted through a large distance, right? So even though I don't have to use my puny nerd arms to move this very hard, I have to move it through a huge distance. I mean, look, I have to move it across this whole distance, right? Even though I get a big force on this boulder out, big F here, even though my output force is huge, the load on the lever is only moved through a small distance. Look at the distance I get out, right? It's just a little tiny baby distance. So that's the idea here. With a lever, you can put in a baby force over a massive distance. That's work. That's force times distance. What happens? The machine, you can think of the machine as the equal signs here. The machine flips it. It flips the script. So what comes out is a giant force, but over this tiny little distance. So sometimes you may want a big output force, which is fine. Sometimes you might want a big output distance. So you got to know what to put into a machine or a lever to get the desired effect out on the other side. So this only works here. This relationship only works if we do ignore small inefficiencies, right? So this will be like heat, friction, which is kind of the same thing as heat. Friction is going to cause heat. Something else we need to ignore is maybe sound. Believe it or not, actually just sound is also something that will cause this issue. So if we ignore all those things and say that, you know, we're not losing too much work from one end to the other, then this relationship will hold, okay? This means that the lever is a force multiplier. So if we have a little f going in, this is going to be giant F coming out. All right. Another simple machine we can talk about is a pulley. Mainly, depending on how you use a pulley, will change what's going on. But if you use a pulley in this most basic sense, it's just going to change the direction of a force being applied. Oops. Give me one moment. There we go. Okay. So when you apply a force to this pulley, or like when you're applying tension to a rope around a pulley, if you're just using it in the most basic sense, it just produces a change in direction, and it's just changing the direction of a force essentially. Um, it can, depending on what you do, you could double the output. That's why I have the and, or you could double the output of a force. So essentially, if we look down here at this figure, part A here, this is the most basic way to use a pulley. You can see that this guy's pulling down on the rope, which is a tension force here. But because of the pulley, on the other side is a tension force up. It's kind of common sense, but you can see how wrapping the rope changes the direction of the tension force. In this situation, the bolt through, or not the bolt, but the pin through the center of the pulley, its axle, is going to act as the fulcrum. So your fulcrum is right there where the axle is on the pulley. And of course, you can see you've got your tension down, your tension up, and that's going to be on each side of the lever arm. So the pulley itself is the radius of the pulley, or the diameter of the pulley is where you're going to get your lever arms from. Now, what's interesting is if you have your rope tied in a solid position and you loop your rope through a pulley this way, notice that you still have your tension pulled up. So you've got tension over here. You're pulling up as well. So you're applying a tension force to the rope. Now think about what this does to your fulcrum though. On the left-hand side, this rope here, it's not moving. It's essentially just hanging there. It's not being pulled or anything. It's essentially stationary. So that's where your fulcrum's going to be. Now it looks weird in this picture, but we have a long lever arm over here to the input tension. That's tension from you pulling up on this thing. And now the output is actually going to be split between the tension from you and the tension from the rope being attached to the roof. Right? So the whole idea is that since we have this rope sort of cradling the pulley, it's equal on both sides, they're going to sort of combine and give us double the output force, the output energy, output work. And that's going to be centered, and it's going to be the main point here is that it's going to be doubled. So you can essentially cut the weight of this box in half. Right? So if you only lift 100 newtons, but you have a 200 Newton box, you can loop your pulley through, or loop your rope through your pulley, then lift this way, and then it'll cut the 200 newtons into just a 100 Newton force you need to apply. Something else to think about is you can actually loop these multiple times, like here in this picture. You can see this is looped 2 or 3 times, and every time you do it, you're essentially reducing the amount of tension you need to apply to the rope to raise some mass, right? But the problem is, look at how much rope you have to pull. So you get to apply less force in this situation. Apply less force, which is good. We want to be able to, we want to be lazy. We want to be able to apply less force, but we have to pull more rope to do it. So the less force we want to have to deal with, the more we're going to be pulling the rope. Something very important to remember is that no machine or device can put out more energy than you put into it, right? So no machine can actually create energy or have a bigger output than input. All right. We sort of talked about this third bullet point, but I didn't interact with the bullet point itself. But essentially, in a machine that multiplies force does so at the expense of distance. That's like I said on the last slide. If I get to apply a baby force, I have to push for so far on the lever to make that work. Just like in the picture here on the right, if I want to pull with a baby amount of force to raise something with a pulley, well, if I loop it through a bunch of times through multiple pulleys, then I have to pull so much rope to get that to work. This is going to lead us to talking about efficiency and just how well these levers or pulleys or whatever machine you're talking about is going to work. So ideal machines, that's important, ideal machines, basically perfect, best thing ever. Ideal machines convert all the input work into output work, right? So that's going to be 100% efficiency. Everything you put in, you're going to get out on the other side. Now, in practice, that doesn't happen. In any transformation, anytime you take some form of energy and go to something else, you're going to lose a little bit along the way. It's kind of like trying to carry a bunch of, I don't know, grains of rice in your hand while you're running. You're going to leave a little bit of a rice trail. It's just so hard to try and make sure they're all there. So in any transformation, some energy is dissipated due to inefficiencies. And this is like through friction and sound and things like that. Actually, in a pulley system, a considerable fraction of the input energy is actually it's lost to friction or thermal energy. That's just because in a pulley system, you get a lot of sliding. It's really hard to keep the rope from sliding sometimes. So that's where you lose a lot of your efficiency in a pulley system. Lower efficiency of machine, the greater the amount of energy that's released as thermal energy. So that makes sense. So if you only had like 10% efficiency, this would actually indicate lots of heat loss. But then if you had something like 90% efficiency, that'd be very, very little heat loss. Now think about how hot the engine of your car gets. The fact that the engine of your car gets so hot tells you that it's not very efficient. So it would be very nice if someone would invent a way to get like a 80 or 90% efficiency out of a vehicle. But right now, you can tell that is nowhere near that close just because of how hot the engine gets. Something to remember is that inefficiency exists everywhere in the world around us. And you basically get some of this heat anytime you have an energy transformation going on, which is essentially all the time. In any transformation, there is essentially a dilution of available useful energy. So if you have all this energy and then you go through an energy process, you have a little less. And if that energy goes through another energy process, you can keep going until over a long time, you essentially run out of energy. So all of that usable energy you start with, once you transform it enough, essentially the only thing you have left is just heat from friction at the end of all those transformations. It could be actual mechanical friction. It could be molecular friction, friction between the molecules themselves. But the way you can calculate efficiency is basically just take what you're left with at the end of the day and just divide it by what you started with. So if you think about it, in a perfect situation, if you put out like 1 joule of energy, and in a perfect situation, you would get out of this machine 1 joule of energy. Well, this is just 1/1, which is 1 or 100%. So this little equation here is set up to where if energy out up top is smaller, right? If your numerator is smaller, it's going to be less than 1. But your numerator can never be larger in your denominator because you can't have efficiency greater than 100%. So you're essentially limited to either 100% or less when it comes to efficiency. So I'm just gonna, for the next little bit, talk about some major sources of energy and show you some situations and places where you can see this energy, and hopefully when you see these, maybe next time you're traveling, some things that we talked about in this module might come to mind. First of all, solar energy is an obvious one. It is a green energy alternative to fossil fuels. We are trying to move away from fossil fuels. What's interesting is just a 1 square kilometer of incoming sunlight. So if you go to like the Sahara, draw out 1 square kilometer, and if you could cover it with solar panels that are very efficient, you essentially, in like very little time, you get the equivalent power of a large power plant. So this does assume very efficient panels. But we're getting there. Panels are actually becoming more and more efficient every year, which is really nice. Another tidbit, the oldest and largest solar complex is in California. I don't know if it's still the largest, but it's definitely a sight to behold. It's the Desert Sunlight Solar Farm. If you fly into LAX or Burbank, you can actually see it from the plane, and it's incredibly bright. What happens is they put out all these mirrors, and you can see the mirrors here. And essentially what it does is all these mirrors redirect sunlight into the central tower, and they use that sunlight to power generators. If you see this on a very bright day from an airplane, it is very bright. I've seen it myself. It's blinding, even from like that distance in an airplane. It's insane. But in addition to solar farms like this starting to pop up, we've been using solar power for a long time because spacecraft, the satellites I use at my job at JPL, they're solar powered. You can see here on the International Space Station, they rely a lot on solar powered sails that they can retract if they need to. That's actually how they're installed. They sort of come out like an accordion, kind of. And that's where the ISS gets a lot of their power from. So a lot of, I think even like Voyager 1 and 2, they're even solar powered. As far as hydroelectric energy, this is something we could talk about now because we have the vocabulary in this class to do it. So with hydroelectric power, basically you generate electricity by taking advantage of the water cycle. You get rainwater flowing into rivers and reservoirs, okay? So you get all this rainwater. And if you can dam it up, like we've done here with the dam, you can redirect this into generator turbines. So the whole idea here is that all of this water has some gravitational potential energy. I'm going to write this out. Gravitational potential energy. So we talked about that like 2 lectures ago. It's above some level, right? So if this is our origin, you can see that it's elevated, it has gravitational potential energy. What we can do is we can force that downward. Now, you'll remember that anything with a GPE, gravitational potential energy, GPE, you can turn that into kinetic energy if you drop it or bring it down in height. That's exactly what happens here. Change this real quick. We use the gravitational potential energy from that bank of water. We turn it into kinetic energy in the generator. And then that's actually where we get our power from. So we have the outgoing power, outgoing electricity from the kinetic energy in that generator. And if you're interested, this is a dam. It's the Kariba. I don't know how to pronounce it. I think it's somewhere in Africa. Um, this is actually the largest dam on record in terms of just water storage. So if you're curious as to what the largest dam looks like, that's a picture of it. Of course, I do have a link if you want to read a bit about it. You can download these lecture notes and just click on the link. Uh, Obviously, fossil fuel is a source of energy. So fossil fuels would be like coal and petroleum, which is essentially gas, like you would put in your car. So this actually comes from uh, decomposition of organisms, so dead crap from a long time ago underground. Uh, as all that biological material decays, it builds up this goop that you can actually burn. It's very flammable, and that's where you get your energy from. It's from the burning of that chemical storage in those fossils. Do keep in mind that when you burn that, it does lead to CO2 emissions and some other stuff, but the big thing is CO2. That's carbon dioxide, and that's essentially what drives global warming. So the burning of fossil fuels produces CO2, which is a driver of climate change. Unfortunately, this is some of the most widely used energy in the whole planet. So hopefully the world can actually transition away from this at some point. If you're interested about the breakdown and where greenhouse gases in general, mainly CO2, but also methane, things like that come from, you can see over here in this figure from the EPA, transportation sector is actually quite large. Almost 30% of these emissions come from burning fossil fuels in your car. Followed right behind that is power generation. So coal-fired power plants, gas burning power plants, that kind of thing. Something interesting to think about is wind energy. Wind energy is essentially just caused by the Earth being heated up by the sun. And since it's not heated evenly, since it is a sphere, you sort of get temperature differentials. So we'll do a delta temperature. And that's actually what drives large scale wind patterns is actually just wind is temperature differences. And that temperature gradient is actually what sort of pushes the air around. And that's where you get your wind from. So if you strategically put generators up in the sky where this wind is blowing around, essentially put up a windmill, you can use that to turn turbines and actually generate electricity. But you are limited to places where the wind is sort of strong and steady at all times. And if you look up here at this figure, basically purple, orange, red, and purple are really good places to have wind turbines. So it turns out that actually in the Midwest, there's a really big potential to have wind turbines. We could power quite a bit of the US with some strategic placed turbines there. And if you've been up to App State or Boone in general, you've probably seen their wind turbine. It's not a great turbine. It doesn't power a whole lot. I think, I'm not sure, I can't remember, but I think it can power or provide enough power, I think, for like 13 homes or something. I don't know. It's not very big, but it is sort of used for like instructional purposes, not necessarily they're trying to power all of campus with it. So a lot of times, if you're a Boone local or familiar with the area, you'll hear people say like, "Oh, it's not even that good of a turbine." It's like, well, yeah, but they sort of teach with it. Um, if you're interested in like being around one of these, you can actually just drive up. You can drive up to it, literally where this picture was taken. You can just park and walk up to it. It's no big deal. If you're interested, you want to go see it. I encourage it. We can also take these windmills and put them in the ocean or in rivers. The whole idea of tidal energy, basically you can put in turbines beneath the surface of the ocean or a river where tidal currents are strong and the water isn't too deep because you need to get back down there to service them. So essentially you get the same effect. Instead of using wind, you're using water flow. The good thing with tidal turbines is quiet because they're underwater and they're out of view. So trying to put in wind farms, usually a lot of people complain about the looks of the wind farm, but you sort of get around that if you put in tidal turbines. So you'll notice that this plot here, it kind of looks like almost like a wind graph. You've got the wind flow, but this is actually water. And you're looking at where water flows are the strongest and most consistent, and that's where you'd want to put your wind turbines. And they even, you can look at this picture here, they even look similar to a turbine that you would like put up on a wind farm or maybe a small turbine at your house. If you're interested in wind energy, I do have a good link to PNNL. They're one of federal labs here in the US that actually does some research into this stuff. They've got a good article here if you want to read it. Other obvious forms of energy is essentially atomic and nuclear energy. We've got hydrogen, hydrogen fuel cells, you've probably heard of that. Hydrogen is like the most plentiful element in the universe, and it's also used in rocket fuel a lot. There's a possibility that we're going to be looking at zero emissions aircraft, which will be powered by hydrogen. Essentially, to get hydrogen, you also create just oxygen at the end. We'll talk about that in just a second. So that's why we would say it's sort of like a zero emissions source of fuel. But hydrogen itself is not an energy source. You sort of have to do some stuff to it, put some energy in to turn it into a fuel. So do keep that in mind. You got to put some energy in. Essentially what you can do is you can take just a regular car battery or any battery. You can do this at home if you wanted to. You could just take a battery, drop in the positive and negative terminals into water. What you're going to do is you're going to create, and I can never remember which one's which, but you're going to create hydrogen bubbles on one side and oxygen bubbles on the other. So you can cap this and catch it. And if you do this, it doesn't take a lot, but if you do this, you can catch it in a thimble or just a little cup, catch the bubbles. You could actually light it with a lighter and it will like form a small explosion. So it doesn't take a lot of these hydrogen bubbles to actually make a small explosion. So please don't do this yourself. Just watch a YouTube video if you're interested. I don't want you to blow your fingers off. You can literally just with crap around your house make a small hydrogen fuel cell and capture your own hydrogen if you want to. Beyond hydrogen, we do have some nuclear energy sources. So like uranium, plutonium, these are actually radioactive. So that's why they're actually a source while hydrogen is not. Since they're radioactive, you can actually collect that radioactivity and use it to generate heat. Yeah, and then the last source we're going to talk about is geothermal energy. This was becoming really big, I think, when I was in high school. Yes, I believe so. You usually see geothermal sources of energy and geothermal power plants in places like Hawaii or anywhere where there's volcanic activity. But applications are possible elsewhere. And here's just one example from your book. It's called Dry Rock Geothermal. And essentially how this works is at some location, you drill a hole through hydraulic fracturing, you pressurize water and send it into this space, and you make a bigger space. That's where this big cavernous thing comes from. So you have all this water in here. Now, because it's close to the Earth's or closer to the Earth's core, and it's deeper underground, you get heat from the Earth. That's going to superheat your water, essentially to the point where once you dig your second hole, it gets so hot that it turns into steam and then comes back up. So the idea is that you're just going to send water down, like you can see here. Well, it looks like the water's going down on this side. So you're going to send your water down, and then you get your steam up. And you sort of form this closed loop using the Earth's heat. And that's how you turn the turbine. So you've got a turbine up here, and that's what you want to turn. The whole point of every single one of these types of energy, whether it was, well, not solar, solar's different, but like wind, the geothermal here, the hydroelectric, the burning of fossil fuels, all of these, the point is to just turn a turbine. Once you get enough energy from something to turn a turbine, you have a motor, you have an engine, you can generate electricity. So that's even like with nuclear, like the big nuclear power plants and the uranium and plutonium, they heat up water and turn it into steam and use that steam to turn a turbine. All of these are just trying to turn a turbine. And that's where your energy comes from that you use in your daily life when you turn on like a light switch. It's generated from a turning turbine somewhere. But you may not even be able to see the turbine. You can see, this is one of these dry rock geothermal power plants right here, and these are actually kind of small. I guess I'm not sure, but I guess somewhere in there's a room you can walk into where there's a massive turbine. Um, one little last point I want to make is that there's something called recycling energy, and this is essentially where if you have, well, let's just read it first, and we'll talk about it. It's basically just the idea of where you could use waste energy from other processes. For example, power plants, obviously, they generate electricity. So if you have a coal-fired power plant, right? So here's my power plant. It's going to generate electricity, right? So we have power lines. It's going to generate electricity, but it also generates a lot of excess heat. So you've got this heat, you've got this steam. Maybe they're burning coal to heat the water to turn the turbine. So what you can do instead of just letting the heat go out, you can actually channel that heat into other structures. You can actually heat the homes in the neighborhood. So now you get a twofer. You get electricity plus you get heat for homes instead of just letting that heat go out into the universe. So that's the idea of energy recycling. And hopefully it's becoming more and more popular. So that's going to be it. Here's just a few links that I talked about in regards to those sources of energy. And that's going to finish up our conversation about energy. We'll hit these topics again when we start talking about nuclear physics later on near the end of the course. So next up will be rotational motion. And oops. And let's see. Yeah. And if you have any questions, as always, feel free to reach out and ask.